Hi folks, welcome to Chapter 9 of Math 8. Many of you have already finished Chapter 8 quiz. Please make sure you do that if you haven't already done so. Chapter 9, along with later on Chapter 10, looks all about linear relationships. That word linear refers to a line, a relationship that we can plot on a graph that will come out to be a straight line. So we already looked at topic 9.1, which was about describing patterns. So we saw various graphs and their values plotted on a table of values and had to practice describing those in various ways. It could be even as one number increases by 1, the other variable goes up by 2. So I have a little bit of a review for that, and after that we'll be looking at expressions and equations. Everything for Chapter 9 will be just in this one video. Okay, so here is a graph about bunnies, one of our noblest creatures in nature. We're counting their ears, and so we see our x-axis at the bottom here with bunnies. As we add bunnies, we see the number of ears goes up by 2 per bunny. So this would be known as our controlled variable, and the number of ears is responding because we are making the decision to add bunnies, and the ears go up by 2. It's impossible to just add the ears separately, add one ear at a time, right? So the bunnies, we can control exactly how many we have. So we see it going up at a 2-to-1 ratio here. There we go. And so I've plotted this on a table of values. So we see here when we have 0 bunnies, of course, 0 ears. And as we go up by 1, you'll see, then we have 2 more ears for each one. So I just went down to 5 bunnies, 10 ears in total. So we'll look at how to write that as an expression. There's a slight difference between an expression and an equation. The expression is a statement that is just referring to how you could figure out one variable. An equation will actually have an equal sign and will have both variables in it, both your x and your y. And if you're given one, you can then figure out what is the unknown other variable by isolating it. So we'll get to equations later. So I wrote an expression here for the number of ears that we have based on our number of bunnies. So you always want to write, what do your variables actually mean? Because yes, you might solve for x, you might solve for y, but if you don't know what that means, what's the point, right? So in this case, y is going to be our number of ears. That was the one going up and down on the y-axis. X is the number of bunnies. So we're writing an expression for the number of ears. And that will be simply 2x. Because whatever we have, whatever our number of bunnies is, multiplied by 2, will give us our number of ears. So the nice thing about an expression or an equation is that you don't have to take the time and the space to write a giant table of values and count your way down it, or to draw a massive graph. You can just enter in the number, simplify, and then you have your answer right there. So in this case, I took a number that actually wasn't on our graph. I took 17. If we have 17 bunnies, how many ears do we have? So all you have to do to simplify is simply put in 17 for x, substitute that, do the multiplication, and it comes out to be 34 total bunny ears. So that's a look at how you might do an expression. Before we go a little bit further, I've got a special treat for you. I'd actually like to give you a little mini tour of my house and meet a special guest. And no, I'm not defying the quarantine protocols. This guest has actually been with me the last month. It's my great aunt Maggie. She was visiting from Nigeria, and with all the COVID, her flight was canceled. She's having trouble getting back to her own country. So I said, Great Aunt Maggie, you're my favorite great aunt named Maggie. So of course you can stay with me. And wait, I think she is baking cookies downstairs. Oh, her famous apple raisin cookies. Okay, let's go meet Aunt Maggie. She loves young people. She believes you guys are the future. Okay, let's go meet Aunt Maggie. Okay, so there's my lovely office. Lovely quilt on the wall. Some family photos. Oh, there we go. No photos of Great Aunt Maggie on the wall, unfortunately, but you'll meet her soon enough. Wait a second, that's weird. Why is my door open? I always keep it locked. I'm like the opposite of Full House. That's strange. Yeah. Aunt Maggie, do you want to meet my students? Aunt Maggie? That's weird. Maybe she's not in the bathroom. Just let me just a second here, guys. There's nothing really downstairs to do. Aunt Maggie, are you there? That's really weird, guys. She wasn't downstairs either. I'm gonna. And the strange thing, I could smell those cookies. I don't see any cookies here. This is really weird, guys. Wait, what's this? This is a note. Whose writing is this? It says, if you ever want to see your great Aunt Maggie again, leave $100 in an unmarked envelope under the bridge, plus $10 for each of her cookies you want to save. Love, Anonymous? What kind of sick person kidnapped someone's great aunt? My great Aunt Maggie, she's been kidnapped. Look at this ransom note. Guys, I'm really upset about this. I don't know if I can continue our lesson. Oh man, great Aunt Maggie. Like, where do we even start here? I'm gonna try just for you guys though, because I know you're working so hard at home. Wait a second here. There is something we can do about this. This is a linear relationship. Yes, okay, let's go upstairs. This is our big break. It's our lucky day. Okay, so we've got ourselves a linear relationship, right? Because it's $100 to save Aunt Maggie, plus $10 for every cookie we want to save. So we can make that on a table of values and figure out an expression and an equation for that. Okay, here we go. So, for our x, we're going to save great Aunt Maggie. That's a sure thing here. But our variable, the thing that's going to change, is how many cookies we save. So x is going to be our number of cookies. Y is going to be our total cost, because the cost is responding to how many cookies we're saving. So x is number of cookies. Oh man, turned out not to be such a bad day after all. Okay, so I'm not going to draw, a table of values could go on infinitely, right? Based on, well, how many cookies she has at least. So if we didn't save any cookies, how much would it cost again? Let's take a look at that note. Okay, it would be $100, right? So if we save 0 cookies, God forbid we save 0 cookies, $100. And then if we save 1 cookie, that is $110, right? Because it's 100 for Aunt Maggie plus 10 for the cookie. So 1 cookie is 110. Stands to reason then 2 cookies will be 120. And 3 cookies will be 130. Okay, so we've got this table of values here. Okay, so now what we're going to do is we are going to write an expression. We need to write an expression to figure out what is cost. How do we figure out the cost based on any number of cookies? So it's going to be 100. We know there's $100 for Aunt Maggie, right? Plus how many dollars per cookie? 10, and that'll be 10x, right? Because we have the $10 times our number of cookies. So that is going to be our expression for cost. And now the thing is, with expressions and equations, the general practice is that you are going to put your term that has the variable in it first. In this case, we figured out our constant, the constant of 100. We put that first because that's what we wanted to figure out, the starting cost, but it's just the way we like to have it presented. It's not wrong, usually, to put the x later, like we've done here, but it just looks better to have the x first. So our expression is going to be 10x plus 100. Okay, so let's say, for example, we wanted to save 24 cookies, a couple dozen cookies. Aunt Maggie does not go around just baking 3 cookies, right? So let's plug in 24 for x and see how much that would cost to save Aunt Maggie and 24 cookies. Okay, so here we have 10 times 24. We've replaced the x with our 24 cookies. And I said what our variable is right here. That's otherwise you would always write let x equal so you know what x actually represents. So 10 times 24 plus 100. So 10 times 24 is 240 plus 100, and that goes down to 340. And it may seem tedious, especially if you have a long equation, to write out everything plus your changes each time, but you want to do just that, because otherwise you're going to end up losing something, losing part of the equation, and all of your work is for nothing. Okay, so those are a couple examples of expressions. Now, how would an equation look different? We're going to write an equation to show the value of y, to show the value of the cost of saving Aunt Maggie and any given number of cookies. So it's going to be the same expression, except instead of 10x plus 100, it's going to be y equals 10x plus 100. Okay, so let's say in this case, we already figured out if we do the math to find 24 cookies, it would be the same. It would give us the same number, the same value there, but it would say y equals 340. So that's how it would work, just the same if we're just solving for everything that's on that same side of the equals sign. Now, well, let's say, though, we have been given a cost, and we need to figure out how many cookies would that rescue. So let's give a big number. Let's go with $2,000. So our y is $2,000 equals 10x plus 100. So this is not quite so neat and tidy, because we have our x. We only have one variable now that we've substituted for y, but we need to get the x by itself to figure out how many cookies we have. So in this case, what are we going to do first? Are we going to divide by 10 to get x just as an irregular x, or are we going to subtract the 100 to get rid of that? Because remember, with an equation, whatever we do to one side, we have to do to the other. And the hard truth of it is, you're going to have to do the subtraction first. You might wonder why. Why can't we just divide each side by 10? Well, you can't, because with this side here, you would have to divide the entire thing by 10. It becomes a little bit messy because you have two different terms. So we're going to do the subtraction first. It really is essentially the reverse of bad math when you are isolating a variable. Those are the steps you want to carry out to get the variable by itself. So we're going to subtract 100 from each side. So you're going to write all of this out. So 2,000 minus 100 equals 10x plus 100 minus 100. And you know what? It might seem a little tedious. Why can't you just say 10x equals 1900? You do want to show your steps. You want to show step by step so it's easy to follow along for whoever's marking it, but also for your own sake so that you don't slip along somewhere and slip up and make a mistake. It happens to all of us, right? So now we're at 1900 equals 10x. So right now x is multiplied by 10. How do we cancel out if something's multiplied by 10? We divide by 10, that's right. So we divide, remember, each side by 10. Because it's an equation, those two sides, that statement says these two sides are equal. If you don't do the same thing to both sides, then they're no longer equal, and your equation is invalid. Okay, so we divide 1900 by 10. That becomes 190. 10x divided by 10 is just x. So 190 equals x. And remember, when we go up to our values, x is the number of cookies. So if we have a nice statement at the end, when the ransom is $2,000, we will save 190 cookies. Yes. Plus Great Aunt Maggie too. Okay, so that's a nice little introduction there to both expressions and equations. You can see there's really not a huge difference between them. Equations are just more flexible because in this case, if you're given the number of cookies, you can figure out the cost by plugging in what you know. If you're given the cost, likewise, you can plug that in and figure out the number of cookies. But getting the practice there is important for getting the variable by itself, whether you're having to add or subtract on one side or dividing on both sides. Okay, so that is it for Chapter 9, and in case you're worried about Great Aunt Maggie, I want to assure you, of course, I don't have a Great Aunt Maggie, at least not anymore.